Greetings and welcome back. So what we're going to take a look at today is the Unit 5 final exam review. Unit 5, the topic area is the periodic table and some trends or patterns that appear. There's a number of words that kind of relate to position on the periodic table, and some of our trends sort of describe behavior of atoms as a result. So we won't get too deep into the details about the key terms here in this assignment, but it is important to know that key terms sometimes help you answer questions. So just make certain that you are familiar with the key terms. You can check the answer keys posted to double check your work related to the language here. And let's get right to work. Let's hide my face here. Be a little more comfortable doing this. So let's see, we want to shut that video off. What do we do? Right, video panel. There we go. Okay. So first series of questions here, a whole bunch of questions about location on the periodic table: noble gases, alkali metals, halogens, alkaline earth metals, transition metals. So let's take a look at how we spoke about how you could do that easily in class. Made up this silly little rhyme here: all alligators trim hairy nostrils. They relate to positions. So the all relates to this region right here, are alkali metals. Alligators, the next position, alkaline earth metals. Trim, the next position, are transition metals. Hairy are halogens, and nostrils are noble gases. So we're just looking at all alligators trim hairy nostrils and the position on the periodic table. So we go back to the assignment, what we're going to find. Let's get the markup tool going here. That noble gas would be our neon. Alkali metal would be the element sodium. Halogen, well, there's actually two answers here. Fluorine and chlorine are both halogens, both in group 7A. Alkaline earth metals, also two answers. Barium and magnesium are both alkaline earth metals. A transition metal, that's that big collection right here in the center body of the periodic table. All of those would be classified as transition metals. So if we're looking at the grouping of those that were provided, the transition metal in that would be copper. Representative element. Easiest way to know if something is a representative element is to know where the transition metals are. Any element that's not a transition metal in the inner body here, kind of highlighted in purple, if it is in a group that we call an A group, that's what our representative elements are in an A group. So when we go back to look at the assignment, the only element located in an A group would be potassium there. Experience is the weakest effect from shielding. So let's talk about this one. I have a little drawing we can use. Lithium, lead, copper, and cesium. Lithium, because it's in period 2, would require 2 rings. So lithium requires 2 rings if we're going to visualize a model of it. So let's do that. Let's go to this little drawing tool here and 2 rings. Let's call this one lithium, Li. Okay, what else did we have? We had lead, copper, and cesium. So lead would require how many rings? Let's see, lead. Lead would need 6 rings. Cesium would need 6 rings. Copper would need 4 rings. So we're looking at trying to answer a question related to size of atoms, or it's actually kind of related to size of atoms, but shielding effect relates to these lower energy levels, right? Remember, the outer energy level is called valence level. So when we're looking at this, lithium only has 2 levels. So lithium only has 1 level of shielding, this lower energy level. So the weakest effect from shielding would be the smallest of those atoms. So lithium, when we look at those choices, since lithium only sort of requires 2 rings to visualize its model, right? Lithium is our best of choice. My apologies about this distraction here. That's not really relevant. So experience is the weakest effect from shielding. We can mark up lithium because that would be the smallest of all of those atoms, and you don't have a lot of shielding effect when you have small atoms. Has the greatest nuclear charge? Well, that's just looking at the number of protons in the nucleus. So sodium, aluminum, silicon, magnesium. So we go to our periodic table. Sodium, aluminum, silicon, magnesium. Let's do that. Sodium. Let's clean up some of our markings here. Aluminum, silicon, magnesium. Sodium, aluminum, silicon, and magnesium. So greatest nuclear charge, 14, right? Silicon has 14 protons, right? So silicon has the greatest nuclear charge. So we'll highlight silicon. Has 3 valence electrons. So we'll go to the periodic table. Anything in group 3A, right? This region right here, something in there would have to have 3 valence electrons. So gallium is a member of that group. Has 4 energy levels with electrons and 1 valence electron. So a couple things we can look for to answer that one. So let's clean the table up a little bit. Eraser, 4 energy levels. So we know we're going to have to be looking at something in period 4, but 1 valence electron, group 1A. Period 4, group 1A, well, that should be the element potassium, which is one of our choices there. Forms an anion. Anion stands for a negative ion. Only nonmetal atoms make anions. Phosphorus is the only nonmetal atom. Forms a cation. Only metals make cations. So barium is the only metal in that list. Remember, if you're reviewing your periodic table, your metals are over here on the left of the staircase. Your nonmetals are to the right of that staircase. So your metals make cations, your nonmetals make anions. Experiences the greatest effect from shielding. So now we want to know which of these is the largest of atoms that would have the greatest number of shields. I believe bromine, when we look at the periodic table, bromine is located right here. It needs 4 energy levels. So it would have 3 levels of shield. Chlorine, fluorine, oh, maybe iodine, right? So iodine would need 5 energy levels, right? So it would have 4 rings that act like shields. So the biggest would have the greatest effect from shielding, and the biggest atom in those choices is our iodine. So we'll mark up our iodine, a nonmetal, while we're looking at the zigzag line on the periodic table. The element that would be a nonmetal would be carbon. All those others are to the left of the staircase. The largest atomic radius. One thing we said you can do when you get your periodic table on an assessment, you write the words low on the bottom, large on the bottom, opposite corner, small up at the top. So large atoms are down near the bottom, right? The further you go to the right in the same row, the smaller atoms actually get. So let's mark up our choices here. We have barium, chlorine, phosphorus, cesium. So let's just put a quick mark for each of them. Barium, chlorine, phosphorus, and cesium. Well, barium and cesium are definitely the largest. If you were drawing models, you'd need 6 rings, but barium being to the right of cesium a little bit is actually a little bit smaller, because as you move to the right, the atoms actually get smaller. So smallest of those 2 choices, right? We're looking for the largest atomic radius. So the largest atomic radius would be our cesium atom. So here we go. We mark up cesium. Highest ionization energy. Now we go back to our periodic table. The words low, lower left corner, high, upper right corner. Those will mark regions where we find our patterns that relate to electronegativity, ionization energy, electron affinity, or electronegativity. So when we're looking at this, this says highest ionization energy. Let's clean up the choices here so we can mark our periodic table, and we'll mark our choices here. We got nitrogen, nickel, magnesium, rubidium. So let's mark those up. Nitrogen, nickel. I know rubidium was one of the choices, right? Rubidium. And what was that last choice? Magnesium. So Mg. And again, what are we looking for? In this case, we're looking for the highest ionization energy. Closest to the top right, right? That would be our element called nitrogen. That would have the highest ionization energy. So our choice turns out to be nitrogen. Lowest electronegativity, cesium, fluorine, chlorine, silicon. Let's mark them. Clean it up a little bit and we'll mark them. Cesium, fluorine, what else was there? Let's go back and check the list again. Chlorine, silicon. Chlorine, silicon, and in this case, it's asking for the lowest electronegativity. That would be closer to our lower left region. Cesium has a very low electronegativity. So our choice turns out to be cesium. Highest electron affinity. Now we just look at the opposite corner for the word high. We got sodium, oxygen, nitrogen, potassium. So sodium, oxygen, nitrogen, potassium. So we can mark them up just so you can see it. Nitrogen, sodium, and potassium, oxygen. And again, what this one is asking for is highest electron affinity, right? This right here, oxygen, closer to a region where we have the word high, right? So our high electron affinity, right? That would be our oxygen. I keep wanting to put that up there. My apologies. So let's mark that guy up as oxygen. Largest atomic radius. Well, if you were building atoms, you'd look at how many rings. Well, a couple of these are ions. So magnesium versus the magnesium ion. Remember, metals give away electrons. So metals are going to lose their whole outer ring. So a magnesium ion is smaller than a magnesium atom. So we know that can't be the largest. Chlorine compared to magnesium. So let's compare chlorine and magnesium. So chlorine and magnesium, let's mark that up. Here's our chlorine. Here's our magnesium, right? So magnesium has 3 rings, right, as an atom, and 12 protons. Chlorine is going to have 3 rings, but 17 protons. So that attraction between the nucleus and the outer electrons is going to be much stronger because of the greater nuclear charge for chlorine. And that's actually going to make magnesium, right, our largest atomic radius. Most reactive metal atom, well, our most reactive element down here that is a metal happens to be francium. So really the closest to that position of those choices is really what we would look for. The most reactive based on position, rubidium is closer than any of those. The most reactive nonmetal, we'd look in the sort of the opposite corner. The opposite corner would be up here at fluorine. Remember, we ignore the noble gases, these guys here, because they tend not to react. They have their complete octet. So closest to fluorine is what we're looking for. And when we look at that, we would see chlorine, right? That guy right there would be the most reactive. Okay. So let's move forward at our assignment here. Again, now we're looking for halogens, noble gases. Again, we go back to that. All alligators trim hairy nostrils, and that will allow us to locate the region that those elements lie in. So for our halogen, right, position E is where the halogens are. Maybe we can make that a little bit bigger. Our text box so we can actually read it. There we go. Noble gas, that's in position A. Transition metal, that's position C. Alkali metal, That would be position D on the periodic table, and alkaline earth metal, position B. Smallest atomic radius, quick reminder, remember what our markup says we're going to do? When we get our periodic table, we're going to regurgitate writing the words low and high in the right position. Low goes in the lower left-hand corner. And you know that high is just going to go in the upper right-hand corner. And then we can also write the words large versus small. Large is going to go down here on the lower left-hand corner because it's an L word. Small will go in the upper right-hand corner. So smallest atomic radius up here where the word small would be, right? Letter A is going to be our best choice for that. Highest ionization energy. So we're going to be up with near the word high, right? High ionization energy. So we would take a look at the highest ionization energy, right? Would be letter A, closest to the position high. Lowest electronegativity, way down low, right? Close to the position low. You might answer B. I might argue that D is a better answer, only because D has to lose one valence electron, but we're not trying to be tricky here, so. Good conductors of heat and electricity. So we just want you to mark up whether or not this is a property of a metal or non-metal. Metals are conductors. Brittle in the solid state, those are non-metals, right? Metals are not brittle in the solid state. Metals are malleable. They will flatten out into thin sheets. So that property, malleable, belongs to metals. Almost always solid belongs to metals. Many are gases, belongs to non-metals. Tend to lose valence electrons to form ions. Metals behave like the chili peppers. They want to give it away, give it away. Now give away them valence electrons. Those are metals. Tend to gain valence electrons, give it to me, but right, they want to gain those valence electrons, non-metals. So how many electrons would a barium atom have? We'll go to our periodic table. Barium's in group 2A, right here, group 2A. Barium's located in this grouping. That's how many valence electrons it would have, right? So it would have 2. How many valence electrons would a nitrogen atom have? Because it's in group 5A, that would have 5. Now we want to rank list in descending order. And that means largest to smallest. So let's go to our periodic table. Hydrogen, phosphorus, potassium. Let's mark them up. Hydrogen, really small atom. Phosphorus, potassium, and what's the last one? Aluminum. All right, so we want to be in a descending order, it says. So descending needs our largest to be first. So the most rings would be K. After that, right, we want to be further to the left, right, because that's where the larger atoms are. So K, A, L, P, and then finally H. So K, L, A, L, P, H, K, A, L, P, H. Right, largest to smallest, there they are. Ascending order of ionization energy, magnesium, nitrogen, strontium, carbon. Let's pick a different color. Let's go to our periodic table. Magnesium, nitrogen, carbon, and strontium. So this is supposed to be in an order of ascending order. So lowest to highest. So the lowest, right, would be strontium, then magnesium, then carbon, then nitrogen. So lowest to highest, strontium, magnesium, carbon, nitrogen. Let's mark it up. Strontium, magnesium, nitrogen, carbon. Descending order of electronegativity. Chlorine, sodium, magnesium, fluorine. So let's see, chlorine, fluorine, sodium, and magnesium. So we're looking at the ones marked in yellow right now. Right, magnesium. Okay. And we go back to the list and it asks for descending order. So we want the highest electronegativity down to the lowest. So highest would be near the top right position. Fluorine, chlorine, magnesium, sodium, right? So fluorine, chlorine, magnesium, sodium, there goes our list. Fluorine, chlorine, magnesium, sodium. Which of these is the largest in ionic radius? Well, what I did is I looked at how many rings we might have for each. So for a sulfur atom or sulfur ion, right? Sulfur ion, we go to the periodic table, we find sulfur. I'm gonna mark that guy up here, sulfur right here. Sulfur, the ion would have 3 rings and 16 protons. 3 rings with 16 protons. So sulfur, 3 rings, 16 protons, right? So what we're looking for is the largest of these atoms, right? So the size is going to be related to how many rings and how many protons attract that last ring. So the more protons there are, the more attraction there is. I think what you're going to find is the one that is closest to it would be potassium. So let's just look up potassium. Potassium would normally have 4 rings, but as an ion, it loses the outer ring. So we're looking at 3 rings, 19 protons. So for potassium, we have 3 rings, 19 protons. Well, that's going to be smaller than sulfur. So our answer turns out to be sulfur here. Which element has the greatest shielding effect? It's going to be our largest atom, right? It would be our element gallium, right? More rings makes more shields for electrons. Why is a copper atom smaller in radius than an iron atom? Well, let's just take a look at that. When we look at copper and iron, copper right here, iron in the same period. So to draw a model for each of these would require 4 rings. 4 rings, however, with 29 protons is smaller than 4 rings with 26 protons. That nuclear charge inside the copper atom causes greater attractive force for the valence electrons, and it shrinks the copper atom. Copper atoms are smaller in radius than iron atoms. Even though they have the same level of shielding, copper atoms have more nuclear charge, and that creates a stronger attraction. So for magnesium and calcium in number 13, how can the atomic radius be used to describe why calcium is more reactive? Well, let's compare calcium and magnesium. So calcium and magnesium, right? They each have 2 valence electrons. They're each in group 2A. However, magnesium is a smaller atom. So magnesium attracts those valence electrons with greater attractive force, making calcium more reactive. So that's how we use atomic size to sort of explain that. And our last few choices here. Really what I was hoping you do is I was hoping you'd look at a number of things. So if you count the number of rings, 1, 2, 3, this element has to be in period 3, but it has to have 1 valence electron. Period 3, 1 valence electron. Period 3, right here. Markup tool, let's get that going. Period 3 with 1 valence electron, right? That has to be our element called sodium. Period 3, 2 valence electrons would have to be something called magnesium, or 12 protons. So what we're looking at, you see we have 12 protons. We have 3 rings, period 3, 1, 2 valence electrons. So 2 valence electrons, right? That's our element right there that we would call magnesium. So magnesium is the identity. We look at letter B, 19 protons, 4 rings, 1 valence electron, that becomes potassium. Letter C, 2 rings, 4 valence electrons, well, that would be carbon, right? Carbon also has 6 protons. And lastly, letter D, 3 rings, 7 valence electrons, while only chlorine can have that. Also, chlorine has 17 protons. So I hope you found this review useful for final exam review, Unit 5. Until the next time, this is Mr. Brewer.